Dear students, today we will discuss some articles from the topic oscillations. The articles we are going to discuss are periodic motion, rotatory motion, oscillatory motion, linearization and differential equation of linearization. These articles will be discussed in brief, and then we will discuss the MCQ points related with these articles and some sample MCQs on these articles. The first one, periodic motion. The motion which repeats after equal interval of time is called periodic motion. Or alternatively, we can say that the periodic motion is defined as the motion which repeats after equal time interval. The time interval after which the motion is repeated is called period of motion. Represented by capital T. Now, we will discuss two types of the periodic motion. One is rotatory motion. Rotatory motion is a motion in which the object moves along the circular path or along the arc of the circle. Example is motion of the earth around the sun, motion of the moon around the earth, the spin motion of the earth about its own axis. All these motions are periodic motions and they repeat after equal time interval. For example, earth takes 365 days or 1 year to complete one revolution around the sun. The earth spins about its own axis in a time period of 24 hours. So these motions are periodic motions and the path is circular path or path may be arc of the circle. For example, the motion of the magnet placed in uniform magnetic field and setting to vibrations. The motion of the pendulum of the wall clock is also rotatory motion in which the path is arc of the circle. The second motion is oscillatory motion. In oscillatory motion, the motion is confined between two fixed points. These two fixed points are called extreme positions, and midpoint of these two fixed positions is called mean position or stable equilibrium position. Oscillatory motion is defined as to and fro motion. Along the same path which repeats after equal time interval. The example of this oscillatory motion is the vibrations of the string which is stretched between two rigid supports and disturbed from its equilibrium position. The vibrations of the air column in a pipe when a vibrating tuning fork is held near the open end of the tuning. The vibrations of the prongs of the tuning fork whenever it is hammered on the rubber pad are also example of oscillatory motion. So, this is about the different periodic motions. Now we will discuss one special type of the oscillatory motion, that is linearization. The oscillatory motion can be represented by the equation f is equal to minus k x raised to n, where n has value 1, 3, 5, 7 and k is positive constant. In this if equation, if n is equal to 1, the motion represented by this equation is called linearization. Or linearization can also be defined as the SHM, in which the restoring force acting on the particle is directly proportional to its displacement from the mean position, and the restoring force acting on the particle is always directed towards the mean position or stable equilibrium position. The definition of the linearization is defined as a periodic oscillatory motion along a straight line, in which the magnitude of the restoring force acting on the particle is always directly proportional to its displacement from the mean position, and the restoring force is always directed towards the mean position. And this condition can be mathematically represented by the equation f is equal to minus kx, where k is a positive constant. Called as force constant. The negative sign in this equation indicates that this direction of restoring force acting on the particle and its linear displacement from the mean position are always oppositely directed. If we represent this graphically by taking displacement along x-axis and force is also along x. When the displacement x is positive, that is moving away from the mean position, the restoring force acting on the particle is negative, that is directed towards the mean position. When x is negative, that is the particle is moving towards the negative extreme from the mean position, the restoring force acting on the particle is positive, which is directed towards the mean position. So whatever may be the position of the particle during the path, the restoring force acting on the particle is always directed towards the mean position. This is the theoretical part related with the definition of the linearization. Now we will discuss some MCQ points of this equation, which are useful in solving the equation. The first thing is the proportionality constant K is a positive constant. Second, it is called force constant, and this force constant K is given by f by x in magnitude. That is, this force constant can be defined as the restoring force acting per unit linear displacement of the particle from its mean position. The SI unit of this force constant is Newton per meter. CGS unit is diameter centimeter. The dimensions of this force constant are m raised to 1, L raised to 2, sorry, m raised to 1, L raised to 1, T raised to minus 2 divided by L raised to 1. So it becomes m raised to 1, L raised to 0, T raised to minus 2. So these are the dimensions of this force constant. Now, for the knit and J, this force constant K is referred as spring constant. In case of the motion of the spring and load system oscillating simple harmonically, the restoring force acting on the spring is say F, and the X is the deformation in the spring from its equilibrium position. Then the once again equation becomes F is equal to minus K into X. Once again, this K is force constant, however it is labeled as spring constant. This concept of the spring constant is not for the CET. It is in the books of the CBSE syllabus, NCERT books. So it can be asked for the NEET or JEE exams. This spring constant K will be large for the stiff spring. If the spring is soft, then the value of the K is small. This is the first thing about the values of the spring constant. Then this spring constant is also inversely proportional to the length of the spring. And the MCQ can be asked on this part like that. Suppose that the spring of length L is divided into n parts. Each of length small. So length of each part of the spring will be L by. Now the spring constant K dash will be equal to n times original value of the force constant or spring constant. This should be remembered. Now, the second MCQ point about this spring constant is the combination of the spring during the oscillation. If the springs are connected in series, then the effective value of the series combination will be equal to sum of the spring constant of the springs connected in series. Sorry. Reciprocal of the effective value of the parallel combination will be equal to 1 by K1 plus 1 by K2 plus dash plus 1 by K. And if the springs are connected in parallel, then K effective will be equal to or parallel combination K1 plus K2 plus dash 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 plus K. These are the MCQ parts. Now by combining these two parts, the different MCQs can be prepared. For example, a simple MCQ. If a spring of length L is divided in two parts having length in the ratio 1:2. This is the given part. Now the first question can be asked, that is the spring constant, value of the spring constant of the first part of the spring. K is spring constant, or is the spring constant of spring. Now as the lengths are divided in the ratio 1:2, the length of the first part will be L by 3 and second part will be 2L by 3. So the first answer we can find out for the force constant of the first part of the spring will be equal to 3 times K. The second question can be asked, what is the spring constant of the longer part of the spring? Say it is K. Then by using this equation, we can have value for the K2 as 3 by 2 times K. Now the third, the ratio K1 by K2 or K2 by K1 can be asked. Finding this can be found out by using values of these, and it will be equal to 2:1. That is 3K divided by 3 by 2K. So it becomes 2:1. The next question can be asked by increasing the difficulty level. Suppose that these two parts of the spring are connected in series. What will be its effective value of the force constant of the series combination? Or these two parts are connected in parallel, then what is the value of the effective force constant of the parallel combination? In this way, the same concept, that is, the force constant is inversely proportional to length of the spring, can be used to solve the different MCQs related with these force constants. The difficulty level is gradually increased. What is the force constant of the smaller part of the spring? What is the force constant of the larger part of the spring? What is the ratio of this longer part to force constant of the longer part to force constant of the shorter part? Or vice versa, or in the reverse. Then difficulty level is slightly increased by using the combination, that is series combination of these two parts or parallel combination of these two parts. So if we study the basic part, then this can be helpful in solving the different MCQs.